Okay, so in this video we're going to go over the struct section of the book. I have it open, have my editor, but right now we don't need that. Let's just make this a little bit bigger. Using structs to structure related data. A struct or structure is a common data type that lets you name and package together multiple related values that make up a meaningful group. If you're familiar with an object-oriented language, a struct is like an object's data attributes. In this chapter, we'll compare and contrast tuples with structs, demonstrate how to use structs, and discuss how to define methods and associated functions to specify behavior associated with a struct's data. Structs and enums, discussed in Chapter 6, are the building blocks for creating new types in your program's domain to take full advantage of Rust compile time type checking. Ooh, that was a mouthful. All right. And here's where we have code. Let me just get rid of this because I know it's not needed. Defining and instantiating structs. Structs are similar to tuples, which were discussed in Chapter 3. Like tuples, the pieces of a struct can be different types. Unlike with tuples, you'll name each piece of data so it is clear what the value means. As a result of these names, structs are more flexible than tuples. You don't have to rely on the order of data to specify or access the values of an instance. To define a struct, we enter the keyword struct and name the entire struct. A struct's name should describe the significance of the piece of data being grouped together. Then, inside curly brackets, we define the names and types of the pieces of data, which we call fields. For example, and this is what we're about to write, shows a struct that stores information about a user's account. I'll keep main here just because we should have a main. Struct user curly brackets, and then now we have the fields username, and we just give it a type, give it a comma, email, comma, sign in count U64, okay, active bool. That looks about right. To use a struct after we've defined it, we create an instance of that struct by specifying concrete values for each of the fields. We create an instance by stating the name of the struct and then add curly brackets containing key value pairs, where the keys are the names of the fields and the values are the data that we want to store in those fields. We don't have to specify fields in the same order in which we declare them in the struct. In other words, the struct's definition is like a general template for the type, and instances fill in these templates with particular data to create values of that type. All right, so what they're saying is give us instructions how to instantiate a struct. And the example right here says let user1 equal user, which is the name of the struct right here. Curly brackets, and now we fill in the fields, and we have to specify the name of the field. So say email, right? We know this is going to be a string. So one thing to note is what they were saying earlier. The order of which we fill this in doesn't matter. We just have to make sure all the fields are filled in. And have someone at example.com, comma, and it looks like the naming convention or the way you instantiate a struct is very similar to the way you defined it. So that's not difficult to remember. String from some username 1, 2, 3 You gotta make it active. It's a Boolean. True. One more field. Sign in count. Make that 1. And yeah, I believe we have just created our first instance of this struct, the struct user. Alright. To get a specific value from a struct, we can use dot notation. If we wanted just the user's email address, we could use user1.email wherever we wanted to use this value. If the instance is mutable, we can change a value by using the dot notation and assigning into a particular field. And below shows us how we go about doing this. Alright, so the first time I went through this section, I made a mistake. And the mistake was I didn't see that this was mutable here. So if you want to change a variable or a field on a struct, you make the instance of the struct mutable, like they did here, and like they did here when they changed it. They used the dot notation to say user1.email equals another email. And to show that this works as expected, let's print this out. Print line user1.email. Building. And here we go, another email. So yeah, if you want to modify your struct, you make the instance of that struct mutable, like they did here. The second thing they wanted to show us, let me get rid of this line, is a builder function. So right now they created a function that returns an instance of a user. So function build user string username string, and we say explicitly that we're going to return a user. And because this is an expression, well, with any expression, if it's the last statement in a function, then it will return. So that's what they demonstrated here. You can do that with structs. Email is equal to email. Username is equal to username. Active, set that to true. Sign in count, set that to 1. Do not put a semicolon at the end, it should return. And just to check it out, let's do that here. We'll call build a user, send in an email. It has to be of type string, right? So string from, I'll just call it email. And then the next variable that we pass in is username, which is also a string from, and I'm just gonna say username. And that is a long line. Could have just wrote that above it. But one thing I want to see real quick, let's print something out. Print email username. Email username. User1 dot email. User1 dot username. Oh, expressing can be simplified. Huh. Maybe they'll go over that in a second. Active bool. Field is never used. That's a cool warning. So if a field in a struct is never used, it will let us know, and then we could probably just get rid of that field. Count is also never used. But what I'm looking for is the print. Here we go. Email and username, right there. So we'll print it out. We use the dot notation as demonstrated here. User1 dot email, user1 dot username. That seems to work. I am really curious about this simplified. Report cases where field initialization shorthand and they have the RSC that is linked. Okay. And here we go. It makes sense to name the function parameters with the same name as the struct fields, but having to repeat email and username fields names and variables is a bit tedious. If the struct had more fields, repeating each name would get even more annoying. Luckily, there's convenient shorthand, and I can already see down here that the shorthand is just say email, just say username, seemingly because the name, the struct field, and the variable name are the same. Let's confirm that. Using the field init shorthand when variables and fields have the same name. Yeah. So because the parameters names and the struct field names are exactly the same, we can use the field init shorthand syntax to rewrite build user so that it behaves exactly the same but doesn't have the repetition of email and username. And we already did that over here. Run it just to confirm. Still runs. Yeah, I'm just gonna skip this paragraph. It's just saying what is already set up here. Creating instances from other instances with struct update syntax. That's interesting. It is often useful to create a new instance of a struct that uses most of the old instance's values but changes some. You'll do this using struct update syntax. Okay, so what they're saying is at times it is useful to, when you have a struct, right, and you want to create a new struct or a new instance of this struct, but you don't want to change all the fields. You just have some fields that are changing, not all of them, maybe like one or two. So instead of creating a new instance altogether and filling each field out from scratch, you can use the first one as a boilerplate essentially, and then only change what you have to change. That's seemingly what this is. First, listing 5.6, that's here, shows how we create a new user instance in user2 without the update syntax. We set new values for email and username, but otherwise use the same values for user1 that we created in listing 5.2. So here's how we do it without the user update syntax, or sorry, struct update syntax. So we're saying we can say let user2 equal user. So we're just creating it from scratch for the most part. User's down there. Give it a semicolon at the end. Let's fill in these fields. Email is going to equal string dot from another email. Oh, another at example.com, comma. Username is also going to change. I don't know why that's not aligned. Username, string, from another username, 567. And here's where we're going to copy user1's information. So user1 dot, is it active? Same as user1. And for the sign in, same thing as well. User1 sign in count, and voila, we have user2. And we just print that out. Run that real quick. We have user2 information. So that's the old-fashioned way, or explicit way, I should say. Now, using struct update syntax, we can achieve the same effect with less code as shown in listing 5.7. With the with the syntax ... that specifies that the remaining fields not explicitly set should have the same values as the fields in the given instance. Okay? So what they're saying is, using this ... syntax, we can say all the rest of the fields, the one that we haven't mentioned explicitly, which in this case is sign in count and active, should be equal to user1. And that should compile. And for clarity's sake, let's print out the other two fields. This is going to be sign in count, so user2, well, let's make it active. Dot active, and user2 dot sign in count. Print out all four, and we see the active is true and sign in count is 1. The code in listing 5.7, this up here, creates an instance in user2 that it has a different value for email and username, but has the same values for active and sign in count from fields from user1. Yeah, that's true. This is pretty straightforward stuff. Using tuple structs without named fields to create different types. You can also define structs that look similar to tuples, called tuple structs. Okay. Tuple structs have the added meaning the struct name provides, but don't have names associated with their fields. Rather, they just have the types of the fields. Tuple structs are useful when you want to give the whole tuple a name and make the tuple be a different type than other tuples. And naming each field as in a regular struct would be verbose or redundant. So this is like a mini struct, seemingly. To define a tuple struct, start with the struct keyword and the struct name followed by the tuples in the tuple. Followed by the types in the tuple. For example, here are definitions and usages of two tuple structs named color and point. I think we're not gonna use this again, so I'm gonna erase all of this thing about user. I'll just get rid of all of this. So if I was to create a tuple struct, starts with the struct keyword, have the name, and then I just fill in the types for the tuple. So this is I32, I guess is RGB for color. I32, I32. And then for another example I have here is struct point. And that is the same. I32, I32, I32. So even though these are the same in terms of the way they look, they are different types. Or yes, they are different types. Let black equal color 0, 0, 0. Interesting. Has a weird underscore in front of it. Not sure what that's about. Let origin equal point 0, 0, 0. I'm not exactly sure why they have underscores instead of telling me what their type is. Maybe that will change in future versions of this IDE. That's interesting to note. Nothing's being used here. Consider using origin underscore. Yes, since these variables are unused, it's suggesting that I should rename them to something that is private or has an underscore in the name. Okay. Note that black and origin values are different types because they're instances of different tuple structs. Each struct you define is its own type, even though the fields within the struct have the same types. For example, a function that takes a parameter of type color cannot take a point as an argument. Even though both types are made up of three I32s, so that is signed integers of 32 bits, signed 32-bit integers. Otherwise, tuple struct instances behave like tuples. You can destructure them into their individual pieces. You can use the dot followed by the index to access an individual value, and so on. Okay, so what they're saying here is what we were saying earlier, is that these two things, even though they have the same signature for the most part, they are still different types. So an instance of color, an instance of point will not equal each other and cannot be used in similar manners. Like if your function takes in a color, you cannot pass in a point, which is what they said explicitly. Outside of that, it's still just a regular tuple. Unit-like structs without any fields. You can also define structs that don't have any fields. These are called unit-like structs because they behave similar to just a brackets, the parentheses, the unit type. I have no idea what a unit type is. So unit-like structs can be useful in situations in which you need to implement a trait on some type but don't have any data that you want to store in the type itself. We'll discuss traits in chapter 10. This is chapter 5. We'll discuss traits in chapter 10. This feature is useful for traits. That's the way they wrote the book. All right, let me scroll down. Ownership of struct data. In the user struct definition in listing 5-1, we use the own string type rather than the string literal or string slice type. This is a deliberate choice because we want instances of this struct to own all of its data and for the data to be valid for as long as the entire struct is valid. It is possible for structs to store references to data owned by something else, but to do so requires the use of lifetimes, a Rust feature that we'll discuss in chapter 10. Lifetimes ensure that the data referenced by a struct is valid for as long as the struct is. Let's say you store a reference to a struct without specifying lifetimes, like this, which won't work. And I'm not going to write this out, but here's what they have down here. So what they're saying is that given that this is a reference, right? When you create an instance of this struct, there is no guarantee that these references to username and email are going to stay alive or live as long as the instance of user it is attached to, which would be an issue because if they were to disappear, then you can't use your user anymore, but your user is still valid of that instance of user anyway. And the compiler won't let you do it. They will force you to specify a lifetime, which they'll discuss in chapter 10, but seemingly lifetimes will probably say, it said here that lifetimes will guarantee that this reference will live as long as the instance of user. In chapter 10, we'll discuss how to fix these errors so you can store references in structs. But for now, we'll fix the errors like these using own types like string instead of references like string slice. that is the end of the first section of structs. It was pretty straightforward until we got to the end. Yeah. Oh, I hope this was useful. Hope you liked it. If you did like it, maybe hit like on the video. Outside of that, peace.